So good morning, everyone. We'll control the weight of the bob. A bob is released from the rest when the string is horizontal. So the bob is released from horizontal position. The string backs, see when it is released from horizontal position, what would be tension at the bottom? Can we very quickly think what will be the tension at the bottom? See this twice this height, velocity will be equal to root 2 GL. I know there why how I wrote that one. Velocity will be equal to root 2 GL. And if velocity is root 2 GL, centripetal acceleration is 2G here. If centripetal acceleration is 2G, tension is equal to 3 mg. Tension will be equal to 3 mg. So what we understand here, when it comes to the bottom, the tension will become equal to 3 mg. And but maximum force it can is breaking strength is equal to double the weight. So it means it cannot even reach this point. Even before it reaches this point, somewhere before this also it is swinging like this. Somewhere before it reaches this point, the moment tension reaches equal to 2 mg, it will break. So what we need to do, we need to find angle theta where it will break. How do we find it out? Let's do that quickly. And let's say the angle is theta. So we know when we have to find tension the string. So if B is the point where it breaks, this angular position here. So at this point, tension has to be equal to 2 mg, then it will break. So we need to calculate tension in terms of theta. And how do we calculate? For calculation of tension here, we need to know the velocity in terms of theta. So first, for this angular position, we calculate velocity. Once we have velocity in terms of theta, we can write tension also in terms of theta and equate tension equal to 2 mg. That's how we are going to solve it. So first we'll find velocity at B. Then using this equation, we can equate tension to 2 mg and you get a solution. So rest is fairly simple. What is velocity at B? See velocity at B here, let's look at this. If I have, what is the height delta H? So this initial height here, it falls to height B. So this is the height by which it has fallen. What is this height equal to in terms of theta? This height is equal to L cos theta. So what is VB square is equal to twice into G into height, 2GL cos theta. So that is VB square is equal to 2GL cos theta. So once we know the velocity at a particular point, now using this particular condition, property of circular motion, we can write it, we can use this equation to find tension at this point B. So let's write this equation. What would be the condition here? So this would be the centripetal direction at B. If this is centripetal direction, T is one force acting, other force acting is mg. So whatever forces are there, we take the centripetal component. And if this angle is theta, T itself already in the centripetal direction, mg component will be equal to mg cos theta but negative. So if I write summation of centripetal component, it will be equal to T minus mg cos theta. That has to be equal to mvb square by L. So on this term, I multiply by m by L. So it becomes equal to 2 mg cos theta. That's the term I get from here. So what is the, and then we equate. So this equals to 3 mg cos theta and tension has to be equal to 2 mg. So when we write this condition, I find the cos theta comes equal to 2 by 3. So when cos theta becomes 2 by 3, that's the time the tension will reach 2 mg and string will break. If we assume that as soon as the tension becomes equal to breaking strength, it will break. So far here, so suppose I add one more thing here. If you have to find what is the tension at point A, can we also find what is the tension at point A as soon as we release? Can we think of what is the tension when the string is horizontal? How do you find tension at point A? Karthik, can you find tension at point A?
Yes, sir.
How do you find tension? Which property we use to find tension at any point? What we need to find tension here?
So forces in centripetal direction is equal to mv square by
centripetal direction. And what is the velocity at A soon after release?
0, sir.
0. So if velocity is 0, if I apply this condition, what has to be summation of centripetal component?
It should be equal to 0.
0. So only one force acting in the centripetal direction, which is tension. So soon after release, the tension here is 0. Okay. So
Yes,
very easily you could have found that also. And suppose we slightly alter this question. Let's see, if we have done one question, it can have several other variations. What other variation it can have? We can also have the same step. In this particular case, it was released from horizontal position. We can also do if this string, if the same string, the same mass is suspended and it is made to oscillate about mean position. So, as we increase the amplitude of oscillation, the speed at the lowest point will keep increasing. Hence, the tension also will keep increasing. So, another question also all of you can try and solve. What should be the angular amplitude of oscillation of M for the string to just break? That also is one more variation of very similar question. Here also again breaking strength being equal to 2 mg. What should be the angular oscillation so that the string just breaks? Yes.
Sir, can you repeat how we got T minus mg cos theta equals to mg cos
Okay.
theta?
At this particular point, okay. Which principle have we used here? We are using this condition. So which two condition? This is centripetal direction, this is tangential direction. So let me draw this figure here also, if you are not clear. So this is the centripetal direction. T is acting like this, other force is acting mg here. Okay, are we clear which is the centripetal direction here?
Yes,
This
sir,
is
I want to
centripetal
know.
direction. Okay, and if this angle from vertical is theta, this angle is theta.
Yes, sir.
So what is component of T in the centripetal direction? T itself. What is component of mg in centripetal direction? We take two
mg cos
components.
theta.
No, mg cos theta, but why minus?
Because they're in opposite direction.
In opposite direction. And so that's what we have done, and this is the most commonly used thing in vertical circular motion. Okay, so we'll continue here. And you think you can easily solve what should be the maximum amplitude for the string to break at the bottommost point? Yeah, so similar
Similar
way,
to
all
the
of you can try.
previous question, right?
Huh?
Similar to the first question, right?
Similar to last question. All are very similar. So we'll look at, see, these are simple question, and actually there's nothing much here. So I thought we're just going through because some of you are still not clear. They're very, very simple question. That's why sometimes my mind which can be tricky. So Bob of, let's look at next question here. This also like a vertical, this also is like a pendulum. At the lowermost point, it is given a velocity of √3 GL. When we give a velocity of √3 GL, will it complete full vertical circular motion here? Jaideep, will it complete full circular motion?
No, sir.
Why not?
The minimum velocity should be √5 g.
√5 GL. And if this is a string, it has to be √5 GL. And this was light rod, in that case, it should have been √4 GL. So we know it will not complete full circular motion. And what will happen, since it will not complete, as somewhere it will stop having circular motion and the string will become slack. So what we need to do, we need to find the angle rotated by the bob before it becomes slack. So what we see from here, so this is the angular position. We mark the angular position like this. So we need to find value of theta. What is the angle it will rotate before the string becomes slack? And what is the velocity at this instant? This is extension of the question. So some of you can try. So we will not do this part here, velocity at that instant. And what is the further height it will rise? So let's do this part first here. And as I mentioned here also, I think some of you recall, so this theta, whether it's more than 90 or less than 90, the basic equation remains same. So what we are going to do now, again, I will write an expression of tension as a function of theta. And what is the condition for a string to become slack? Tension has to become 0. We notice here as velocity is less than √5 GL, it will not complete vertical circular motion, but it is greater than √2 GL. √2 GL is velocity it needs to reach the horizontal position. It will cross horizontal position. And if it has to become slack, it becomes slack only after crossing horizontal position. Okay, so it will not complete. So what is the important point we need to keep in mind? See, it will become slack at a particular point. So just before that point, it has circular motion. Just after the point, it will have parabolic motion. So that's a boundary line. So until string becomes slack, it has circular motion and it will have parabolic motion soon after that point. Okay. So what is the condition we'll apply to calculate that point here? Calculation. So at that particular point, just a point before it becomes slack, it has circular motion and t is becoming 0. That's the condition. That's how we'll find theta. So theta is state when t is approaching 0. This angular displacement and t becomes 0. So we'll write t as a function of theta and apply this condition and equate t to 0. So what are you going to do to calculate tension at a particular value of theta? First, we need to find velocity. Then only we apply this condition here. So first, we'll find velocity as a function of theta. Then we can find t as a function of theta and equate t to 0. We get value of theta. That's our approach. So let's see how do we solve here. So if this is a place here, what is VB square? VB square equal to VA square minus 2GH from conservation of mechanical energy. Every time skipping one step just to save time. We can simply apply conservation of mechanical energy. If this vertical, this height is h, VB square will equal VA square minus 2G into h. But h also is a function of theta. How much is h? H is, we have done, I think earlier also, L into 1 minus cos theta. So we know, so what is VB square? Let's put those values. VB square is equal to VA square, which is equal to 3GL, minus in place, this term also we multiply by 2G and substitute here. It will become minus 2GL plus 2GL cos theta. So if we combine these two terms, it becomes GL plus 2 cos theta. GL had taken out. So this is VB square. We found this is how velocity will vary as a function of theta. So what we have done, since we have to find theta, first we find V as a function of theta. How V varies with theta. Now, once we have V, we can find T also as a function of theta, and then equate tension to 0 to find theta value. So let's find T as a function of theta. This we have found V. Now, what is T equal to? Again, this equation you're going to use. What is centimeter component? We have done it earlier also. By now we should know. It is T minus mg cos theta, theta being angle from the vertical. And this term has to be equal to mv square by L. This like mvb square by L. So this term m into vb square by L means I'm going to multiply by m by L. So this L will get cancelled. It will become mg 1 plus 2 cos theta. So this is the equation I get. What is this equation? This is how T will vary as a function of theta. Now we'll equate T to 0. If I equate to T to 0, I get the value of theta. When I equate T to 0, I find cos theta comes equal to minus 1 by 3. See, can someone think of why is cos theta coming negative here? What does this imply?
Theta is greater than 90, right?
Theta is greater than 90. So this equation is valid even for theta greater than 90 also. So it will not, theta will be greater than 90. So actually if I mark this position, this theta, where this has just become slack, we have found theta value when exactly at this point only it has become 0. Before that, tension was not 0. And this angle is theta here. So this angle theta, I can also write as, you can break theta as equal to, if I call this angle as alpha, theta can be written as 90 plus alpha. So I write theta is equal to 90 plus alpha. So I can get this angle measured from the horizontal. So if I write theta is equal to 90 plus alpha, which becomes equal to minus sine alpha is equal to 1 by 3. Or I get the value of sine alpha is equal to 1 by 3. So I get this value of sine alpha. And once you have sine alpha, I can get the cos alpha also. So this angle at which, so if the angle was given from horizontal also, we could have easily calculated. So that's where it becomes 0. And can we calculate what will the velocity? Can we calculate velocity at this angle here? Yes, we can calculate velocity. How would you find velocity at this point here, where it has become slack? So actually this is a point B which we're calculating, where tension has just become 0. What will the velocity at this point here? We already had this expression of VB square. Only thing in place of cos theta, we substitute minus 1 by 3. We get this velocity, just become its slacks. And do we know what the angle is? Yes, we know this angle also. If this angle is alpha from horizontal, we know this angle alpha. So at this point, we know the vertical component, we know the horizontal component. What will be the motion of this particle soon after this point? What kind of motion? So until this point, how it has moved? This particle has moved like this. It has moved in a circular path of radius L. So here the tension is kept on reducing. Tension has become 0 at this point. And we have calculated this angle theta. We have calculated this angle alpha also. What would be nature of motion after this point? Soon after this point, what would be the nature of motion? What kind of motion this particle will have? Dhanshri, can you tell me what is the nature of motion of this particle after this point?
It would be parabolic.
It will be parabolic. Soon after the moment tension has become 0, from thereafter it will have parabolic motion. So further question we have to ask, what is the further height it will rise from this point here? This height we can easily calculate. Further height it will rise will depend on vertical component of velocity at this point square by 2g. We can calculate for the height and we can do other calculations also. So little more complicated question of similar question, if you look at S.C. Verma and some other books, is also given. Another variation of the question is, what should be velocity at the bottom so that this particle which is connected to the string passes through the point of suspension? So that question becomes a lengthy question. That's why it will not come in mains. But if you are interested, you can try and solve. So you can. So here we have to work back. If this is a property, we can happen. Okay, so we can work back and can calculate that as well. From here onwards, parabolic motion, and then until here it was circular motion. And this is a point where tension has become zero. That's what we have calculated. Yes.
Sir?
Yes.
So how do we know that between the instant where the tension becomes zero and the highest point, tension won't start acting again?
Okay, that's a valid point. But then see why the tension will not start acting again. See what happens when you from this point onwards. If we have to theoretically prove, see why tension has become zero. Another way to understand the tension has become zero because from this point here. Okay, so what would make again tension to be non-zero? Let's see if this is parabolic path and from here I draw a circular path. Okay, I draw a circular path. So what you are saying, if I take this point of coordinate, basically, is it possible to prove that from a point, if I draw a parabola and a circular having a common tangent, y coordinate of circle will always be greater than y coordinate of parabola? That is something mathematically you can prove. We won't prove it, but are you have done parabola now?
Yes, sir.
So is it possible to prove that if I have a parabola and a circle, and we can, from this equation, if I from here onwards, we can write the equation of parabola here. I can write the equation of circle also, the circle, and I can take in this also as a coordinate system. I only think what I need to prove for same value of x, y coordinate of circle will be greater than parabola. We can prove that point also, but we'll not get into this. Yes, it will move inside. It will not go outside.
Sir?
Yes. And
Sir,
what will happen? Other reason I can tell you also. See, when it moves here, it will have a varying radius. We have done in case of parabola, if you recall, if you have a parabola at different points, it have different radius. You recall that one we did 2 days back?
Yes, sir.
Which point is as point A? Which point is the radius lesser? At the point of projection, or as it moves from A to B? What happens to radius of instantaneous radius circular motion? Actually, radius keeps decreasing. Curvature keeps increasing. So just understand from here also, at this point, radius of curvature of parabola is same as circular radius. After this, what is the radius of curvature of the parabola? It is always less. Since it is radius always less, its curvature is more. If the curvature is more, it can go outside the circular path only when the curvature is less, not when the curvature is more. Do you understand this point?
Yes, sir.
So why curvature is that we can easily prove. If you recall, just check that one also. When we have a parabola, at the point of projection, as it moves to the highest point, radius of circle will keep on decreasing. So here also, the radius everywhere, this radius will be smaller than capital R. If the radius is everywhere smaller, it will move more and more inside. So we can, number of ways we can find out the value, but yes, it will not go out. It will not become tight again. It will tend to become tight only if the parabolic path is tending to take it at a distance greater than r. That's why I said that's a constraint motion. Okay.
Yes, sir.
You can verify that. Next question here. A small ball is suspended. Let's look at this. A small spherical ball is suspended through a string of length L. Whole arrangement, we have done a similar one. Whole arrangement is placed in a vehicle. So if you have a vehicle moving with velocity v, suddenly the vehicle stops and ball moves in a vertical circular path. And so if vehicle is going, you can actually try also suspend something, keep moving the constant speed and suddenly stop. You'll find because of inertia, this ball will keep moving. And since it is tied to string, it will keep moving in a circular path. If the velocity was very small, it will just oscillate. It will go to particular maximum angular amplitude. and come back, it will keep having angular oscillation. But if velocity is large enough, it may complete full circular motion. Here, so what is given here? It is able to complete a vertical circular path. If the tension in the string at the highest point is tension of the weight of the ball, what is the value of B? So at the highest point, the tension in the string is 2 mg. That's what is given. So based on that, can we find out what is the velocity of the vehicle? So if you start thinking, how is velocity of vehicle is related to tension at the highest point is equal to 2 mg? Let's think back. If tension at this point is given, it means velocity at this point can be calculated. If this velocity can be calculated, velocity at the bottommost point we can calculate it. If velocity at the bottommost point is known, this velocity is nothing but velocity of the vehicle. So we can find that answer. So basically what we are saying here, for the period after vehicle stop, as soon as the vehicle stop, point of suspension comes to rest. And this has same velocity as the velocity of the vehicle. The point of suspension is at rest. And as the tension and velocity are related, for a given tension, first we find out velocity at the top, and then we can find velocity at the bottom, which is the velocity of the vehicle. So that's a scheme of solving this question, and we can rest of it we can easily do one by one. So what we are starting with, see, we are starting with, since the tension is given, we can apply again the same condition. This is centripetal direction. I am applying which condition? Summation of forces in the centripetal direction. Summation of component of forces in centripetal direction is equal to mv square by r. What are the forces acting here? Here forces acting T plus mg here. And both are in the same direction. Both are directed towards center. Is equal to mvp square at this point velocity square by L. T is given is equal to 2 mg. So from when you substitute T is equal to 2 mg, we get the velocity at point P is equal to root 3 GL. So this is the velocity at root 3 GL. So whatever this number is there, plus 4 will be here. So velocity at the bottom will be equal to root 7 GL. And that we can calculate from conservation of mechanical energy also. We can write equation here. See, those who want to do that, again, we can easily write here. So I'll apply conservation mechanical energy between point P and point B and easily get this relationship. And this is the velocity of the vehicle. Okay, next question. Again, our vertical circular motion. And this is something what you have. It could be any shape. This part is smooth. And it basically tangentially connects to a path which is form of a vertical circle in vertical plane. So a cube of mass m starts at rest from point A at height 4r. Then from bottommost point, this is at height of 4r, this is initial point, where r is the radius of the circular track. It slides down the frictionless track. Why friction is important? There's no loss of energy. Otherwise, this loss could have taken place. The force which the track exerts on the cube. So when it is sliding, it is in contact with the track. And because the contact, friction is not there, but normal force will act. So what we need to find? The force track exerts at the cube at first, which point? At point 3. Point 3, at the point 3, the velocity is vertical. So it means this point is, see if I connect to the center, this is horizontal line. So what is the force track will exert on this block at point 3 and also at point 2, topmost point? This is what we need to calculate. So what is this going to here? So that's what we need to do. And if we compare this motion here, in place of tension force, now the tension force has been replaced by normal reaction. But both forces, whether it was tension or normal reaction, both are directed towards center. So as far as motion goes, there's no difference at all. The point of action, let's see, rather than force being like this, the corresponding force because of the track is here, but rest all remains same. So let's see how do we start solving. So suppose I want to find tension at this point. Sorry, not tension. We want to find what force track will exert on this block when it is at this point. That's what we need to find. And since the track was frictionless, the force will be in this direction, N3. That's what we need to calculate. How would I calculate here? Again, I will use what kind of motion the object is having this point. It is having circular motion. And this is the centripetal direction. So again, I use the same property of circular motion. I'll mark all the forces. 1/4 is normal reaction, and second force here is mg. And I need to know velocity at point 3. This point 3 is pretty simple compared to point A. It is lower by what distance here? It is lower by distance 3r. So vertical distance is 3r. If vertical distance is 3r, I can find velocity. Once I find velocity using property, I can find value of n3. That's a scheme. So motion is identical to that of a particle connected to a string of length r with normal reaction in place of tension. That's the only thing. Rest all is same. And in this case, though it is not relevant here, this track right now it is straight track. Had it been any shape, as long as the track is something like this also, it comes like this. As long as track is smooth, when it reaches the bottom, speed will be same. So it doesn't matter if it is inclined, vertical, or curved shape. All those things not relevant. Only the height of this point is relevant, which I hope most of you will understand. So let's solve this question. Okay. So basically, this is a point we need to calculate here. We have drawn this free body diagram, and this is centripetal direction and marked. This is the normal reaction at this point, and this is mg. So we'll use this condition so many times. Velocity at this point is √6 gr. So in this case, if I write this equation at point 3, summation of force centripetal component is equal to mv3 square by r. So what is only this mg has no component, so centripetal force is nothing but normal reaction is equal to m by r into square of velocity. Square of velocity is 6 gr, so which gives you normal reaction is equal to 6 mg. So this reaction here will be 6 mg. What about point 2? So similar way you can do at point 2 also. So point 2 also I need velocity. Velocity, what is the velocity at point 2? Again, I can apply conservation of mechanical energy between 1 and 2. This height is 2r, so this height is 2r left here. So it will have a speed corresponding to delta h is equal to 2r. So easily we can find. So velocity will be equal to √4 gr. And in this case, again, if you write mg and a normal reaction, this is a normal reaction at point 2. And this is mg. Both are acting in the centripetal direction. So they will add up. N plus mg has to be equal to m into square of the velocity divided by r, which is equal to 4 mg. Hence, normal reaction here becomes equal to 3 mg. So they are fairly simple questions. Now we come to some questions. Even if you have a hemispherical surface, if object is placed on the hemispherical surface, it can be either given a negligible velocity. So basically, sometimes the question can be, it is given a very gentle push or very gentle nudge and it starts moving. So very gentle push and nudge means at it start with velocity close to 0. It has to non-zero, otherwise it would not have moved. Or it can be given some extra velocity also. We can give different velocities here. We'll see what is the effect of different velocities given at point A. So here in this case is imagine a smooth hemisphere, and question would be same if it is a smooth semi-cylinder also. Both cases are same. Hemisphere or semi-cylinder of radius r placed on horizontal surface. A small block is placed on the top, is given gentle nudge. What will be nature of its motion? So in this case, some of you might think it will keep moving like this. Will it reach this point here? Will it always keep moving along the surface? Actually, it will not keep moving along the surface. Somewhere after it will move for some distance, at some point it will tend to lose contact with the spherical shell. It will lose contact. The moment it loses contact, it will have kind of parabolic path. So it will not come and reach at the bottom. It will lose contact with the sphere at some point of time. And see, even if you're not sure, let's check whether it will happen or not. So let's assume, because intuitively, I think some of you can intuitively feel it will lose contact. Even if you're not sure also, we can check. Let's assume that it loses contact at a position which is making an angle theta with upward vertical, point B. And if it loses contact, what is the condition I can apply for it to lose contact? Can we tell what is the condition I will apply? If it loses contact, so this point is on verge of losing contact. So if I relate it to slackening of a string, here also what will happen? Loses contact means normal reaction will approach 0. So at theta, normal reaction will become 0. So we'll do something similar to what we had done in case of slackening of a string. So at this theta, first I'll find velocity as a function of theta. Then I'll find normal reaction as a function of theta and equate the normal reaction to 0 to find the value of theta where it loses contact with the surface. Okay, so it will slide off the surface or lose contact with the hemisphere after some angular displacement. So till the moment it is contact with the hemisphere, it will have circular motion. So last point where it loses contact, even at this point also, it has circular motion. I can apply circular motion property. Soon after losing contact, it will begin parabolic motion. Let the angular displacement be theta when it has last contact. This is the last point, which is of the part of circular motion. So this is a boundary where circular motion ends and parabolic motion begins. Let's see that is possible or not. So what is the condition? Circular motion with approaching 0. Normal reaction has to become 0. Then that's what losing contact means. No contact means there cannot be any contact force. We'll apply this condition, but first we'll calculate V at this point. So that's what we need to do. Rest all is fairly simple. And this kind of question also common and important. And any variation we should be able to solve. We need to find velocity at B. How do you find velocity at B? If I have to solve, well, basically, again, this time maybe if I choose this as gravitational reference, I can equate mechanical energy at A to mechanical energy at B. So I'll write this equation, a mechanical energy at A will be equal to 1/2 m VA square if V has some finite velocity plus mg delta h. So what is the height here? Delta h also we can easily write in terms of theta. That has to be equal to 1/2 m VB square. So if any value non-zero here in this particular case, this velocity is given as 0. If non-zero also, this is a condition I can apply. And what would delta h be here? Delta h would be this is delta h. This is r minus this height is r cos theta. So r minus r cos theta is delta h. So r1 minus cos theta. So we find VB square. VB square is equal to 2g into delta h is equal to r1 minus cos theta. So we obtain the velocity at point P as a function of theta. Of course, as theta changes, velocity will keep changing. And now we'll find tension also. How do we find tension? We have done it several times. Now centripetal direction. This is mg and this angle is theta. So I'll resolve mg two component, centripetal component will be mg cos theta. We've seen it earlier, similar to before. So let's write this equation. This equation mg cos theta will be equal to m into mv square by r. So if you multiply basically r term will cancel, it will become 2mg 1 minus cos theta. That's the equation I get here. And when you simplify this equation, I get cos theta is equal to 2/3. So angle cos theta, when cos theta becomes equal to 2/3 and it's a finite value. So even if I was not sure it will lose contact or not, since I get a value of theta, which is cos theta, which is positive, it means it will lose contact before the angle becomes 90 degrees. Had this value come as negative, that would have proved that it will not lose contact on a hemisphere. So this angle, and if V was some other value also, we can solve for some other value of V also. Okay. And one more variation of the question. Let me ask this question. Okay. And see, one thing what we can do, we can give different velocity of V. How do we impart different velocity? We can always give a sharp impulse. And we give a sharp impulse, but just imagine if we strike, see, how do we give a sharp impulse? We can also always think of something like billiards table or snooker table. So we hit with a cue, and cue basically it applies a large force for very brief duration. And during the time this cue remains in contact with the ball suffers very small displacement but very large force. So by striking the object with something like a hammer or with a cue rod, we can give a sharp impulse. Sharp impulse means large force for a very brief period of time. It changes the momentum. It suddenly gives it velocity. So we can give a different velocity. Now my question is, if V0 is the horizontal velocity given, what has to be minimum value of V0 so that it basically slides off the sphere right away? It does not remain in contact soon after this. What has to be minimum value of V0 for it to slide off the hemisphere right away? Why would it lose contact right away? Can we think of an answer?
Root GR.
Root GR. If it is greater than root GR, velocity, when we give velocity, if this V naught is equal to root GR, yes, it will lose contact, it will fly off as a parabola, it will not get in touch. And that's also one question you find many books. And similar variation of the question, and this question also, I'm not going to solve it. This is a part of your assignment. And this also will find fairly easy. It's a simple, exactly the same thing. So slightly it has been changed. So rather than having a kind of a hemisphere, let's say we have a quarter of a cylinder and top is connected to a smooth horizontal surface here. So it is a smooth horizontal surface followed by a circular surface in a vertical plane. Radius is r. And this block is given a velocity, not root gr, is less than that. So it will not slide off right away. Had this velocity be equal to root gr, straight away after reaching B, it would have slid off the surface. So in this case again, so what we need to do here, if this is the velocity here, it leaves the block in the question it is given. It leaves contact at point C. And angular position at the point C measured from upward vertical is theta. Can we calculate theta here? That's what the question is. How do you solve? Very similar as before. Okay. Only thing what change will happen here when I calculate velocity at C as a function of theta. Yes, this velocity also will come into picture. And again, rest all is same. Find velocity at C using conservation of mechanical energy. After finding velocity at C, rest all is simple. I'll use summation of forces in centripetal direction. And since the normal reaction has become 0, had normal reaction been present, my equation would have been something like this. It would have been, centripetal component would have been mg cos theta minus n. Because here the normal force is not centripetal. So a normal reaction is acting against the centripetal direction. That would have been mc by c square by r. So we can simply solve, and it's a fairly easy question, and I should be able to calculate. Now come to some other variations of question. This actually is not in a vertical plane. This question is more of conservation of mechanical energy, work power energy type question. Let's understand here, and we can have several variations of a question. In this case, there are two things here. It's a combination of circular motion and also spring. So far, previous cases, when we applied conservation of mechanical energy, it was only because of gravitational potential energy. Look at this question. A collar B of mass 2 kg. So this is a collar here. Collar is something, is a ring, which is moved. This is a circular ring. It can slide freely on a circular ring. So that's called a collar kind of thing. It could be a bead also. Of 2 kgs constrained to move along a horizontal, smooth, fixed circular track. Pay attention to the fact it is horizontal plane. So right now, if it is in horizontal plane, at all points in this motion circle here, its gravitational potential energy is not changing. Okay, so gravity is not coming into effect. And circular path, this is a circular track here, a LEGO kind of track, and it has radius of 5 meters. The spring is lying in the plane of the circular track. There's a spring here, and it has a spring constant of this spring constant given, and it is undeformed when the collar is at A. So when the collar reaches at this point, the spring is in natural length. Indirectly, it means the natural length of the spring is 7 meters. That's what is given, this distance 7 meters. So this part of the statement implies that L0 of the spring is equal to 7 meters. If the collar starts from B, so suppose the collar was here, you need to pull this collar, you can apply a force here and slide it back, you can pull it and bring it up to here. So you bring this here and suddenly you release the collar here. Now what happens at this particular point, as soon as we release here, this spring is applying a force, which will try to slide and it will move along the circular path. So I hope all of you can visualize what kind of motion it will have. So moment it released from this path, what we need to find if collar starts from rest at B. So at this point, it is released from rest. It is no velocity is given. Velocity at this point is 0. So when it reaches A here, it will reach this point A. We need to find what is the normal reaction exerted by the track on the collar when it passes through A. That's what we need to find. And if you look at this, it's a fairly simple question. See, if we take the whole spring, circular track, and collar as a system. As a system, what are the forces acting which is causing motion? In this case, only force which is doing work and causing motion, two forces are acting. Actually, three forces are acting on the collar. What are forces acting on the collar? Is weight is acting, spring force is acting, and contact force is exerted by the ring. And if you visualize here, it's slightly, maybe some of you can easily understand. The contact force exerted by the circular ring will have vertical component as well as horizontal component. Vertical component of contact force exerted by the ring is equal to mg, and they will cancel out. So we can ignore here vertical components, but we should realize there's a vertical component also. And if there was a friction, even vertical component also would have contributed to frictional force. That's the only importance. And so some of you want to attempt little more difficult question, I can give some more variations of this question, which will make it a little more tricky. But right now, so this is a contact force exerting, but contact force will not doing any work. It will act in the radial direction. Vertical component, yes, it will cancel out due to weight. So we can ignore that one. And horizontal component is acting in the radial direction, is not doing work. So mechanical energy is conserved. So my calculation is fairly simple. To calculate normal reaction at A, since the path of the collar is still circular, it is moving in a circular path, I can still apply property of circular motion. So at this point, if this is centripetal direction and only horizontal force acting at point A, see, two forces could have acted. Which are the two forces could have acted when it comes in? Is spring force and the contact force reaction here in horizontal direction. But when it comes to A, even the spring also reaches natural length. The spring also is not applying any force. The only force acting in the horizontal direction is this normal reaction, horizontal component. Normal reaction has vertical component. I'm repeating again, but we are not worrying about vertical component. We are only looking at horizontal component. So to find the horizontal component here, I just need velocity at A. And we can easily find velocity at A using conservation of mechanical energy. Which are the 2 points I'm applying conservation of mechanical energy to whole system? Initial system is at B, and final system, and it has reached A. So mechanical energy at B is equal to mechanical energy at A. And mechanical energy will have only two parts here, kinetic energy plus elastic energy stored in the spring. So at B, what is the elastic energy stored? It will be equal to 1/2 K times is square of extension. So this is 7 and this is 5. So this becomes 12. This side is 5. So naturally, this line length, inclined length of the spring becomes 13 meter. If the length is 13 meter, unelongated length is 7 meter, its extension is 6 meter. So that's what we write to find normal reaction at A. First, we need to find velocity at A using conservation of mechanical energy. Let's write this equation 1/2 K into square of extension, which is 6, 13 minus 7 square, is equal to 1/2 m into v square, v being the velocity. It is nothing else. Gravitational potential energy has not changed. And when it reaches point A, I could have written potential energy in the spring, but here extension has become 0. Thus, the potential energy of the spring also is not coming into picture. And we find v square is equal to 3600. In most cases, v square is enough. And so when we apply summation of forces in radial direction, equate it to mv square by r. Since we know the v square value, we substitute this, we get this force. So horizontal verb, okay. What is the normal reaction exerted by the track on the collar? So perhaps still, I think I made a slight miss here. I should have added what is the normal horizontal component, because it will have vertical component also. Vertical component we are not bothered. Horizontal component of normal reaction exerted by the track on the collar. When it passes through A, this will be the value. So far, is this understood well? This is something. Okay, now we come to amusement park, which sounds little like a machine in amusement park. Consists of cage of an edge of each arm. And you would have seen, see, basically it is a big circle kind of the Ferris wheel. And from here, small cages are suspended. And these cages always remain vertical. You know, this is something as it goes wrong, because since it is kept loosely connected here, it will always, cage will always remain vertical. So this is something, and this Ferris wheel, and it goes around like this. And typically what happens here, initially it may gain speed, it will get accelerated. After a while, it moves with a constant angular velocity. And when we depending RV, so if it is moving the constant angular velocity, each cage will have same constant speed when it is moving in a steady state. So we are talking about steady state. So this is amusement park, cage at the end of each arm, and it is hinged at O. Then all cages are hinged here. It revolves around a vertical circle of radius R. And this radius is R. And it has constant linear speed equal to root GR. That's the speed it has. And it is a vertical circular motion, but unlike previous cases, the gravity is not coming into picture. Previous cases, what used to happen? Velocity used to change. That's a centripetal acceleration also used to change. Here, velocity is constant. So that's an important point we need to keep in mind. This point becomes important in next question also. So in this case, you're standing in the weighing machine here. And why you're taking weighing machine, God knows. But you're taking a weighing machine to amusement park. And worse still, what you do, you take it to even the ride also, and you're standing in weighing machine, and you're looking at the weighing machine. So if you keep looking at the weighing machine and you record your weight at different position, how would weighing machine reading differ at different points? And why would it differ? Okay, so that's what the question is, and then I'll come in one more variation of the question. So if I take reading at all different points here, in which direction, let's say it is rotating in this fashion, where would I get maximum reading? Where would I get minimum reading? Which 2 points readings will be equal, and why would it vary? That's a question. So first thing, it goes back to question of working of a weighing machine. So if I have a weighing machine, if I stand in a weighing machine, let's see if so this question is also to understand your concept of weight better. If you stand on a weighing machine, normally you get reading as mg. But let's see, this machine is given a horizontal acceleration. Will the reading change? Horizontal acceleration will not change the reading of the machine because the normal reaction will not change here. But if it is given vertical acceleration A0, in that case, the reading becomes equal to mg plus A0, which we have done last week or maybe a couple of weeks back. So only vertical component of acceleration. If vertical component is upward, reading increases. If vertical component is downward, reading decreases. Now let's come to this point. So all the places, let's mark the direction of centripetal acceleration. Every point it is accelerated. When you move in a vertical circle, you are accelerated. Which direction? Magnitude of acceleration is same. What is magnitude of acceleration everywhere? Magnitude of acceleration, centripetal acceleration, is v square by r, which is nothing but g. That's the centripetal acceleration, but different point, it has different directions. This is the direction of centripetal acceleration. So now, where would the weight be maximum? Where the vertical component is upwards and maximum. So this is a point I notice here. Here the vertical component is maximum, upwards. This is a point where I'll get the maximum reading. Which point do I get minimum reading? Where acceleration is downwards. This is a point I'll get a minimum reading. Which point I'll get the true reading? Where this vertical component is 0. This is the point where vertical component is 0. Here I'll get the true reading. And what would the reading be here? This vertical acceleration is g. And so what will happen at this point here? If this is the centripetal acceleration, so normally what are forces acting? Normal reaction and mg. So if I write equation at this point, I could have directly written here from this equation also. The reading will be equal to twice the weight. Here reading will go in 0. What does reading 0 mean? See, actually, if you are moving at through this point, if you're sitting on your scale will show 0 reading, because momentarily you will lose contact with the scale. And some of you can relate it to, see, so if you pay attention, sometimes when you're passing on a road which has a vertical curve, and your curve goes like this, when the car is passing through a vertical curve, sometimes you lose contact with the seat. The reason why you lose contact with the seat is something similar. When you pass through this one, you will have centripetal acceleration. If the speed is greater than root gr, you lose contact with the surface, weight becomes 0. So here, just know that for momentarily, the reading will become 0. That's what will happen in this case here. Okay, and rest all is easy. Okay, I think there's one last question I wanted to do. I missed this one. I think I'll do some other session. This question also important question, a little different question. Okay, I'll stop here. I think this time is up. So this only one question is left, which I wanted to finish today.
Sir?